Next, Hess Law. This Hess Law. This Hess Law explains the quantity of heat absorbed or liberated during the chemical reactions. According to this Hess Law, the quantity of heat absorbed or liberated do not depend on the number of stages involved in the course of reaction. The quantity of heat absorbed or liberated actually depends on the initial and final states. Therefore, one factor which influences the quantity of heat absorbed or liberated is the initial and final states. Initial and final stage. Final stage. Next, the another factor which influences the quantity of heat absorbed or liberated is number of moles. Number of moles. Next, another factor is physical state. Physical state of reactants. Physical state of the reactants. Reactants and products. And products. Another factor is temperature. Another factor is temperature. So, for example, so this is a carbon. Carbon is in the form of graphite. Graphite. We have taken the oxygen. Here CO2. CO2. So, here if 1 mole of the graphite is taken, the quantity of heat liberated is 398 kilojoules. If we change the number of moles of the graphite, automatically the amount of the heat liberated during the course of the reaction also changes. Therefore, the quantity of heat liberated depends on the quantity of the reactants that are participating. Next, second factor is a physical state. So, here in this case we have taken the graphite. Here same carbon let us take in the gaseous state. Here when carbon is in the graphite form, if it wants to participate in the oxidation, first the carbon atoms present inside the graphite, they should separate from each other. For that separation process, they will absorb some amount of the energy. Hence, the remaining energy only will be liberated to the surroundings. But here, when the carbon atoms are already in the free state, without the need of absorbing any amount of energy from surroundings, directly they can release the total stored energy to the surroundings. Hence, here definitely the amount of heat liberated will be much greater than the amount of heat liberated from this reaction. Here let us say usually around 1200 kilojoules per mole will be released. Per mole will be released. Next, temperature. See, when the temperature of the reaction system changes, the quantity of heat absorbed or liberated also changes. Therefore, the influence of temperature can be studied through one expression called Kirchhoff expression. Kirchhoff expression. So, just briefly I will explain the Kirchhoff expression. This is the enthalpy change taking place at one particular temperature. This is NCP dt. Therefore, if we change the temperature of the reaction, the enthalpy change involved in the reaction also changes. Therefore, in order to know the change in enthalpy along with the temperature, you have to integrate this expression. Here in this case, we are assuming the Cp of the reaction system is almost remaining constant, but practically it is not constant. Therefore, T1, T2. Therefore, here T1, T2. Therefore, H2 minus H1. This is NCP T2 minus T1. So, with this expression, see, if you know the enthalpy change at one temperature, we can calculate the enthalpy change at the other temperature. This is a lower temperature, higher temperature. Enthalpy change at lower temperature, enthalpy change at the higher temperature. Therefore, if you want the enthalpy change at the higher temperature like del H2 is equal to del H1 plus NCP T2 minus T1. With this expression, we can calculate the enthalpy change at the higher temperature.